right, welcome back. Yeah, so a question came up in chat, which is having a template for, say, prom arrays or PLA arrays. I don't know how I would ask a programmable logic question in this format. Perhaps I would do an analysis question where I would show you a fuse map and ask you to, describe the equations that it represents or the function that it performs. Asking you to draw a fuse map, normally, I would give you a piece of paper with a blank fuse map and you would just mark the connections, but that doesn't work unless you have a printer as well as, a way to take a picture, which I'm not going to ask people to do, so I'll have to figure out how to do that. Cool. Alright, so let's dig deeper into this notion of sequential circuitry. So circuitry with a memory. And we started with the idea of a pair of inverters cross-coupled like this. And this will hold a bit value, either a 1 or a 0, but we can't control what that bit value is. So then we switched to the idea of cross-coupled NOR gates with a pair of inputs and an output Q. And a NOR gate, as soon as any input is a 1, the NOR output's a 0. So let me call this input R, and let me call this input S. And the observation we can make is if R equals 1, then Q is equal to 0. If R is equal to 0 and S equals 1, what happens? Well, if S is 1, the input to this NOR gate is a 1, the output will be 0. You have a 0 on this input and a 0 on the R input. The OR is 0, the NOR is a 1. Q will be equal to 1. So if R is 1, the device resets. If S is 1 and R is 0, the device sets. If R equals 0 and S equals 0, Q equals whatever the previous value of Q is. So you can actually build this pair of NOR gates, hook them up like this, and you get this really interesting device, which looks like this. Pair of inputs, R, S, and one output, Q. And if I want to store a 1 in this system, all I do is I take the S input and I pulse it. And normally R and S are both low. Okay, if I want to set this device, I want to store a 1, I just take S and I pulse it. If I want to store a 0, I take R and I pulse it. Okay, so what does this look like in a timing diagram? So here's R, here's S. Made R way too long. Okay, but here's time. So S starts off low, R starts off low, and let's just suppose Q starts off low. We don't know what Q is, but I'm just going to pretend that it's low. Okay, suppose I raise S and then drop it back. Q is going to go high. And Q will remain high until I pulse R. And once I pulse R, Q will drop. And if I pulse R again, well, nothing changes because Q is already low. And if I pulse S, Q raises to a 1. All right, so there's a sample timing diagram for this SR device. And here's the really interesting thing about it. If I look at, say, this point in time, R is a 0, S is a 0, Q is a 1. If I look at this point in time, R is a 0, S is a 0, Q is a 0. If I look at this point in time, R is a 0, S is a 0, Q is a 1. So knowing that S and R are both 0 does not tell us the value of Q. Sometimes it's going to be a 1, sometimes it's going to be a 0. Okay, this means a truth table is not sufficient to describe the behavior of this device. Because if I try to make such a truth table, well, it's clear if S is 0 and R is 1, right? For example, right here, the Q goes to a 0. And if S is 1 and R is 0, then Q goes to a 1. But when S and R are both 0, we don't know what Q is. Okay, it could be a 1 or it could be a 0. What it is the same value that it was when we were in this case or in this case. Okay, so this is sequential behavior. And so sometimes we write something like this. And this Q plus is basically looking at like the new or the next value of Q. And this is saying the current value of Q. So if S and R are both 0, then the new value of Q will be the same as the old value. New value meaning the value after, you know, the bits have chased themselves around this loop. Okay, so it's stable. Having both inputs 1 is usually forbidden. Because the way we interpret this is you raise this line to reset the device, you raise this line to set the device. What would it mean to raise both of these lines? It says I want to set the device and I want to reset it simultaneously. That's kind of meaningless. Okay, but if we look at the actual circuit, you can see that any time R is a 1, the output is going to be a 0. So this will actually be a 0. And the book uses the term reset dominant. Meaning if we both ask to set and reset the device, it's the reset that wins. But usually in SR device, we don't think about both inputs being 1. Okay, this is the building block from which everything else comes. So if there's questions about this, this is a good time to ask them. And it's a very different circuit from anything we've done in 120 or so far in 250. So this is called an SR latch. The book may call these SR flip-flops. I call them latches. It's just a terminology thing. This is how, so question, is this how all memory works? This is how a lot of memory works. The really fast memory that is sitting inside your CPU chip, the really fast cache memory, this is how it works. Okay, cross-coupled NOR gates or something like that. The really dense memory, the 16 gigabyte memory card that you get for a few bucks and put into your laptop, does not work like this. That memory works basically with little tiny capacitors that hold a small amount of charge and have to be refreshed. It's a lot denser because you only need one capacitor per bit, whereas this you need to build 2 NOR gates basically. Solid state drives are interesting. They're non-volatile memory, so that's a different technology. And building a device like this, right, once I take the power away and I put power back on, there's no telling what state it's going to be in. It really kind of depends what's the initial output here, and then that output will be preserved. So yeah, a little different from SSD. But DRAM the stuff that makes up the bulk of the memory, that's built using capacitors basically. SRAM, static RAM, that's built using this kind of approach. So cross-coupled inverting logic devices. All right, so SR latches are a building block, and they're kind of cool, but you know, they're not the most convenient thing to use. If you want to store a 0, you have to pulse this R line and then drop it down again. If you want to store a 1, you have to pulse this S line and drop it down again. Well, now we're just going to start going wild, and we're going to start sketching out a bunch of circuits built on top of an SR latch. Okay, a more useful device might be what's called a D latch. And a D latch looks like this. We have a data bit, and we have a line called load, and we have an output Q. And what we'd like to do is, you know, put a data value on here, and when we want to store that into our latch, we just pulse the load line. And once the load line is high, whatever the value of D is going in, that gets stored inside this box. And when the load line goes low, that bit is trapped in here. And now D can change high and low, doesn't make any difference. The bit is stored inside this latch. Okay? And so the behavior of this might be something like this. So maybe at this point our load line pulses high, and at that point our latch becomes a 1. And it will stay a 1 as long as the load line doesn't change. So these changes to the input D over here, no effect, right? It's ignoring them because the load input is a low. But when we raise the load to a logic 1, now whatever value is on the D input, that becomes the Q output. And if we kept that load line and we let the D input change, right, we would actually see the output matching whatever that input value is. And let's say we drop the load line over here. Well, at that point, the current D input, that's what's latched into our device. Okay, so pretty quirky device, right? When load is high, the output matches the input. When load is low, the output is stable, completely ignores the input. And this is a more useful device because what do we typically want to do? We want to say something like, you know, I equals 7. Or I equals j times 2 inside a computer, which means we want to calculate some value over here and load it into a section of memory. Well, this equal statement would say basically once you've got these values sitting on the D input of a bunch of latches, let's go ahead and raise the load line for a moment. Load those values into the set of latches called I, and then drop the load line. And now we've set I equal to, you know, some particular value. That's a simplified view of how computers work, but not entirely untrue. Okay, so D latches are nice. We can build a D latch from an SR latch pretty easily. Here's how we do it. Here's our SR latch. Here's a D input. Here's a load input. If our load line is 1 and D is 1, I'm going to hit the S line. I'm going to set the device. If our load line is high and our D input is low, I'm going to hit the reset line. And then this is just going to be the Q output. So this whole thing looks like a D latch, but it's really just an SR latch with a bit of extra circuitry. And if you work through this design and think about, you know, inputs like that, you'll see that this does exactly what it's supposed to do. Because basically if the load line is low, this is a 0, this is a 0, S and R are both 0, your latch is stable. If your load line is high, either S or R will be driven high depending on whether D is 1, that drives S, or D is 0, inverted to a 1, that drives R. Let's see, question. So would D be kind of like what's on the bus in a computer, and load just copy whatever is on the bus to the place in memory? Yep, basically that's it. Because if we picture this D latch, right, there's D, and there's Q, and here's load. Well, we can take a bunch of these, D0, D1, D2, D3. We can have outputs Q3, Q2, Q1, and Q0. And we can drive all of the load lines at the same time. And now we can put a 4-bit number in the top, and by pulsing the load line briefly, all 4 bits get latched into these latches, and now we have 4 output bits that are stored. So we can make what's, in this case, a 4-bit register out of 4 single-bit latches. And so yeah, in a computer you have a data bus, which is moving collections of bits from one place to another, and if you want to store those somewhere, you use something like this and load them in. Okay, ready to go deeper? So we're executing an equation in an instruction in a computer that says effectively I equals j plus 1. So we have some register here, which we think of as j, and it's got, you know, a series of outputs. Let's say it's an 8-bit register, so there's 8 of these D latches. There's 8 bits coming out, Q0 through Q7, and we can put this into an adder. And we have another input which we feed the value 1. And we have some sum bits, and let's just say there's 8 sum bits. So this takes the value of j from the Q outputs of the D latches, right? This takes the constant 1, it puts them into an 8-bit adder, right? Maybe 8 full adders, and it produces an 8-bit sum. And we feed that into the D input of a register called I. And it's got a load input, and we pulse that load line. All right, and this will effectively execute the instruction I equals j plus 1. Right, j comes out here, 1 gets added to it, the sum goes into the D inputs of an I register. We pulse the load line, I is j plus 1. Perfect, right? All right, what about this? I equals I plus 1. Now, first of all, if you ever write this on a math test, you're going to get weird looks from your math teacher. Because in algebra, I is never equal to I plus 1, right? That's nonsensical. This is not saying I is the same thing as I plus 1. This is really saying take I, add 1, and put that into the place of I. Okay, so I plus 1 goes into I. It's an assignment. And there's a notion of time here. We want the current value of I plus 1 to become the new value of I. Okay, there's a temporal flow taking place here. Really obvious, but extremely significant. So let's make a sketch like this for what the circuitry would have to do to implement this equation. And this is a very common thing to do in programming. Anytime we have a counter, a for loop, if you've done CSE 121 for example, we're always trying to increment variables. So let's picture an 8-bit register that we call I. And here's 8 bits coming out Q. And here's our adder. And here's our 8-bit number 1. And here's the sum, which is also 8 bits. And that's going to go around to the D inputs on our I register. And we're going to have a load line, which we're going to pulse. Okay, looks a lot like this, except we've got feedback. So the idea is I has a particular value, say it's equal to 5. We're going to take that value 5 and the number 1, add them together. That's going to give us a 6. We're going to load a 6 to those D inputs on those 8 D latches for the I register. We're going to pulse the load line. Bingo, I is going to be 6. I equals I plus 1. No problem, right? Except, depending on how wide this load pulse is, I might be I plus 1, or it might be I plus 2, or it might be I plus 10. Because suppose I equals 5. Okay, the 5 comes into the adder, the 1 goes in here, the sum is equal to 6, the 6 goes around, the D input is 6. As soon as we raise this load line, each of those D latches is going to see, 0, 1, 1, 0, the pattern for 6. That's going to get loaded in here, and this is going to be a 6. As soon as that 6 gets loaded in, the Q outputs become 6. The 6 goes into the adder. The 1 is still going into the adder. The adder, which is a very quick circuit, adds those together and gets a 7. The 7 comes around those wires, goes up here, and goes to the D inputs. If our load line is still high at this point, the D input is going to get loaded in, and the Q output is going to match it. Right? So remember we said as long as the load line is high, the Q outputs match the D inputs. If they drop, it drops. If they raise, it raises. And maybe this load line is really long, and that 7 goes in here. There's your 7. 1 gets added to it, which gives you an 8. And that 8 comes around to the D inputs of the register. And since the load line is still high, maybe we're right here right now, that 8 gets loaded in. And now that 8 comes in here, and the 1 goes in there, and this starts building up to a 9, and maybe at that point the load line drops, and we're done. But I was equal to 5, and we said I equals I plus 1, and now I is equal to 8. Okay, we just crashed our machine. So this is a huge problem. Okay? Synopsis. Basically, as long as this load line is high, whatever's coming on the inputs gets loaded into this latch. And the problem is, if this load line is high for too long and the outputs are affecting the inputs, this might execute multiple times. Now, one solution to this is to keep your load line really short. But how short do you make it? If you just blip this really briefly, it might not blip long enough for these inputs to get loaded. Because maybe you want to do I equals I plus J plus K plus L times the square root of Z, right? And all these things need to get calculated, and it might take a certain amount of time, more than this, for these inputs to be the new value that you want I to have. So you end up playing a timing game. If you make this too short, you don't have a chance to load the new value. If you make it too long, that new value you load can potentially change the feed going into the input, and you end up getting the wrong numbers loaded. And that's a really hard way to design circuitry. Okay? People do this. It's something called asynchronous design. And it's a really interesting research area. So I said, someone asked what exactly makes it crash. Well, I don't know if it crashes. I said that kind of a general hand wavy kind of thing. But if you're saying I equals I plus 1 and I actually increments by 2, chances are something somewhere is going to go wrong, right? And I'm picturing, an entire computer system with an operating system with lots of code running that's managing resources. And if something goes off by just a little bit, these things are usually fragile. I'll give you an example. When I was an undergrad, our school had a computer. Okay, PCs weren't a thing, but the whole school had one computer that was used by all of the engineering students, and there were hundreds of us. A couple of friends and I got permission to have exclusive access to that machine Saturday nights. So Saturday night from I think midnight till 6 a.m. we could lock it down and do what we wanted with it. So I thought it would be interesting to make time run backwards. So in the operating system, there's a piece of code every time that a certain thing ticked internally, it would add 1 to a number, and that number basically turned into the time of day. And so I went in and I just changed one instruction, so instead of adding 1, it would subtract 1 from this counter, because I wanted to see what it would do. And, I did that, and nothing in particular seemed to happen at first. And a few seconds later, I was in my editor, and I was looking at some code in my editor, right? Every time that you hit a left parenthesis, the cursor temporarily goes to the matching right parenthesis, highlights it for 2 seconds, and then comes back. Well, when I did that, it jumped over here and highlighted this, but it never came back to that one. Why? Because it was waiting for 2 seconds to pass, and 2 seconds never passed. Okay? Because time was going backwards. So my editor session wouldn't function anymore. I couldn't type anything. And then my friend who was sitting next to me got some strange error message because something noticed that something had happened at a point in the past that shouldn't have happened. And after about 30 seconds, the system crashed, right? And it's interesting to try to analyze these things and track down exactly what was sort of the fail event. But most operating systems are fragile. Most computer systems are fragile. A single flipped bit is often enough to eventually cause something to catastrophically fail. And certain kinds of conditions, the operating system will notice, hey, something is seriously wrong here, I'm going to restart. And it'll just reboot itself. It gave an improper answer, so it would be called a malfunction, right? Possibly. Yeah, so if you said I equals I plus 1 and it actually added 2 to it, yeah, that's definitely a malfunction. And this, again, is something that can happen when you play around with like overclocking your processors, for example. You might try to do I equals I plus 1 and I doesn't get incremented because your clock ticked before it had a chance to finish the addition. So yeah, those are definitely malfunctions. The load line is what tells the system to keep running for however long the load line is. The load line in this case is saying, now I want you to look at your inputs and remember them. Okay? The output is always getting added to 1 and it's always being sent back to the inputs. But the load line tells this register, this set of D latches, now I want you to look at your input and remember those values. And if I tell it to do that for too long without stopping, right, those values will keep changing and it'll keep remembering different values. Yeah, that was technically a mini computer. It was a computer called the VAX 11780. It was one of the most popular computers of its time. Is it possible to create specialized clocks to have different effects on the circuit? Maybe. What kind of specialized are we thinking of? And what kinds of different effects on the circuit? I mean, I can picture ways where that might be a reasonable thing to do. But in your question is the answer to all of this, because we have not really talked about a clock. And this is asynchronous design, no clock, okay? No synchronization. The way we deal with this is to introduce a clock, okay? And I alluded to this last week, but let's look at the details of this. And this is where we go from what I call latches to what are called flip-flops. So a latch looks like this. D goes in, a load line goes in, Q comes out. And when load is 1, Q is equal to D. So if load is 1 and D is 0, Q is 0. If load is 1 and D is 1, Q is 1. If load is 0, the value of D doesn't matter. Q, which I'm going to call Q plus, is just whatever the previous value of Q was. Okay? Whether or not the output is changing in response to the inputs is a function of the level of this load line. Load equals 1 or load equals 0. So we call this a level triggered device. As long as the load line is 1, the output responds to the input. Okay, and it introduces this potential flaw, this malfunction, where the load line is high for too long. There's a different kind of device, which we can call an edge triggered device. And an edge trigger device looks like this. It has a D input. It has another input that we'll call a clock. And we put this little funny notch here to show that this is an edge triggered input. And here's how an edge triggered device works. If your clock is 0, does not matter what your D input is, your Q output is totally stable. If your clock is 1, does not matter what your D input is, your clock is totally stable. The only time that your output ever changes is when the clock changes from 0 to 1. And at that moment, if your D input was 0, the output becomes 0. If your D input was 1, the output becomes 1. It's triggered on the knife edge of the clock. Very subtle but fundamental difference with a latch. So let's see what this looks like. So let's have a D input. And let's look at a clock. And let's look at the output Q, and let's suppose that Q starts off low. The only time anything happens is when the clock rises from 0 to 1. At that moment, since D is high, the output goes high. And nothing else matters until the next time that the clock rises from 0 to 1. And at that moment, D is low, the output goes low. All of this stuff, completely irrelevant. Even though the clock is still high, the D input is ignored. Okay, that's the fundamental difference from a level triggered device. Level triggered device, as long as this, what we called the load line before it was high, these D inputs would be affecting the Q outputs, right? In this case, it's only the value when the clock rises from 0 to 1. So it's that precise knife edge right there, that's when D gets sampled and adjusts the output. And then all of this is irrelevant. The clock drops, that doesn't make any difference. Clock rises from 0 to 1, there's the edge of the clock. That's when D gets sampled, it's 0, the output goes low. So what does this mean? If we were to build this with a clocked device, where the input is edge triggered, and let's suppose this clock line is really, really, really long, right? And let's go back to our original value of I, which was 5. And this is before the clock hits, right? So I is 5, we take 5 going into the adder, we take 1, we add them, that's a 6. 6 comes around here. 6 is sitting at the D inputs. At this point in time right here, the D inputs get sampled, they get loaded into the device, your output is 6. That 6 goes into your adder, gets added to a 1, gives you a sum of 7. That 7 comes around to the D inputs, but guess what? Those D inputs are now being ignored. And it doesn't matter how much time this clock is high, we're not going to do anything with those D inputs. Your output is a nice solid 6. The clock drops, and eventually at some point the clock may raise again, and at that point the 7 would get loaded in. So each time the clock ticks, I gets incremented by 1. And in between ticks, there's no false increments happening. Okay, this is a synchronous design.
How do you design something mechanically that detects the ticks?
So I'll show you a circuit diagram built on top of latches that will do this kind of behavior. Is that what you're asking? Yeah, I'll show you a circuit diagram in a minute. Okay, so this is synchronous design. This is how most computer systems are built today. Okay, and this is why our computer systems have clocks. The clocks are the things that tick. And they tick at a speed that's fast enough that you get the performance you want, but slow enough that, you know, we're guaranteed once this new value appears in here, there's enough time for it to go through all of its circuitry and all of the inputs to get set up correctly. Okay, we'll talk about timing constraints probably Thursday, and there's a homework question in the beginning of the homework about timing. But it's a engineering question, you know. If you make the clock too fast, things may not have a chance to catch up. If you make it too slow, your computer does 2 things a minute, nobody's going to buy it. So trying to set that timing at the sweet spot, interesting question. Alright, so that's synchronous design. And these things we call flip-flops. So this thing that I'm describing is a D flip-flop. And it's typically drawn like this: input, clock, and an output. And almost always, we usually see these things drawn with a pair of outputs, Q and Q bar. And Q bar is just the complement of Q. And it turns out the way that these things are built, you kind of get this Q bar for free. Right? Why is that? Because whatever your output here is, this is usually the opposite output. So you just take a wire and run it out and call it Q bar, and now you're giving the customer an extra output that can be useful sometimes. Let's see, question: will the PDF booklet material will be on the midterms? The parts that we've gone over, yes. There's more stuff in the text than what we've gone over. For example, compressing K-maps and stuff like that we did not go over. The stuff related to prime implicants we did not go over. Some of the details of different types of logic, CMOS, NMOS, PMOS, we did not go over. So again, look at the homework questions that were assigned. That's a good guide to which parts of the book I might test you on. Alright, so we have D flip-flops. Let's look at how we build one. And like I say, you can build one pretty easily from a pair of D latches, and this is a really clever design. Okay, so let's make a D latch. Now let's make another D latch. let's take the output of one latch and feed that to the input of the next. And this is going to be the output of our flip-flop. And this is going to be the input to our flip-flop. And here's going to be our clock input. And I got a 50% chance of getting this right if I guess, but let me see if I can figure it out. I missed my wire. There we go. Let's try it like this. Okay, so we have a clock which is feeding the inverter going into a load and going straight into the load. Let's say clock equals 0. Okay, so the clock is low. We have a 1 going into this load line, which means whatever D value is coming into the flip-flop is getting loaded into here and is coming out here. And it's sitting right here at this input. But guess what? Since the clock is 0, this load line is low. Okay, so the D input that you're putting into the flip-flop is getting loaded into this first stage, but is not appearing out of this Q output because it's not loaded into this latch. Okay, when the clock raises to 1, you now have a 1 on this load line. Whatever value was sitting here, which was the D input that was being supplied out here, that D value gets loaded in and your Q output now matches D. Okay, so the clock rises, Q takes on the value of the D input. But as soon as that happens, since the clock is now 1, the inverter outputs a 0, this load line is low. And now the value of D at the moment when the clock rose is latched into this device. And any changes to D are completely ignored by the system now because they can't get into this device because the load line is 0. Because the clock is 1, it's being inverted. So now D is wiggling back and forth, high and low. The value in here is rock solid. It's going through here. Q is rock solid. Now your clock drops to a 0 again. And the value out here, right, since your clock is a 0, it gets inverted to a 1. Now these wiggly values coming into the flip-flop finally get loaded into this latch, but guess what? The clock is a 0 now. This device is locked down. So those D values come in, they get all the way to here, but they stop right here. And they don't go into this device, so Q is still totally solid. And the only time Q changes is when the clock raises from 0 to 1 again. So it's really just a pair of latches, each controlled by a clock with a different phase. And this is sometimes called a master-slave arrangement. Okay, you have one device and it's following whatever the other device is doing. And this is how most of these flip-flops are implemented. So this is a D flip-flop. All right, how are we doing on time? We got 9 minutes. We got 8 minutes now. So go through the beginning of the chapter. Find the section where it talks about D flip-flops. Well, let me just show you. So I don't present it like this, and this may be more confusing, so you can read through this, but don't worry too much about it, okay? We'll come to this material later on. Don't worry about this. Don't worry about compressed characteristic table. Don't worry about the K-map. Don't worry about sequential issues. Just don't worry. Still not worrying. Okay, section 4.5, additional flip-flops. So this is the D flip-flop that we're talking about right now, right? Data clock, Q and Q bar. And these transitions happen when the clock rises. Sometimes you want a device where the transition happens when the clock falls. That's called a negative edge triggered device. What do? Just put a bubble on the clock. Just think of the clock as being inverted. Okay, here's 4D flip-flops put together to make a register, right? All the clocks are ticked together. And sometimes these flip-flops have clear inputs. Okay, so here's a clear with a bar on it, right, and an apostrophe. So this is an active low clear input. If you put a 0 into here, the flip-flop gets forced to a 0. So by putting a 0 into each of these 4 clear inputs, we can force all the bits in this register to go down to a 0. So that's just some of the stuff that's going on in here. All right, I'm not going to do that. Let me just show you on paper. There's a few other kinds of flip-flops. One is called a T flip-flop. And a T flip-flop looks like this. It's got an input T, it's got an input which is a clock, it's got a Q, and it's got a Q bar. And its truth table, which is not really a truth table, right, because it's sequential, looks like this. Right, so if the clock is high or the clock is low, it doesn't do anything. And we usually don't even bother listing these two states in the truth table, right? We understand that the truth table is only interesting when Q is changing, okay? So when Q changes from a 0 to a 1, if T is 0, the new value of Q is the same as the old. If Q is 1, the new value of Q is the opposite of the old. That's the main thing a T flip-flop does for us. So it's a toggle flip-flop. Okay, and the toggle flip-flop, if the T input is 0, it doesn't do anything. You can tick the clock a million times, nothing changes. But if T is 1, then every time the clock ticks, the output toggles. It goes from 1 to 0 to 1 to 0 and so on. Okay, that's a T flip-flop. The other one, this is the one we'll probably work with the most, is a JK flip-flop. And I'm not even going to draw the clock here. This is what the system does when the clock ticks. Okay, so when it goes from 0 to 1. So if J and K are both 0, it doesn't do anything. Okay, and this is similar to an SR device. J is like the set line, so if J is 1 and K is 0, clock ticks, the output gets set. J is 0 and K is 1, that's the reset line, clock ticks, output goes to 0. But if J and K are both 1, clock ticks, the output toggles. Okay, so if we were to draw an SR device, right, both inputs 0, nothing happens. Reset line is asserted, output goes low. Set line is asserted, output goes high. Both inputs asserted is considered invalid or forbidden. Okay, that's the flip-flop version of the SR latch that we started with. A JK flip-flop makes use of this extra state and says, you know, if both inputs are 1, let's just toggle the output. And we can sketch circuitry for all of these things just by building on top of a D latch or a D flip-flop. And it's just a little bit of extra circuitry. So we have all these different flip-flops, D, SR, JK, okay? And they're all edge triggered, and they can be positive or negative edge triggered. And you can get chips, right? A 74 LS76, I believe, is a pair of JK flip-flops. So what are we going to do with these things? We're going to build state machines. And let me give you a 60-second picture of a state machine. You're going to have some combinational logic, right? ANDs, ORs, inverters, XORs, no feedback. Okay, just plain old stuff that can be described with truth tables. You're going to have some inputs. You're going to use this combinational logic to update some memory. You're going to take that memory, you're going to feed it into the combinational logic, and you're going to have some sort of outputs. Okay, that's the basic system we're going to be working with for most of the rest of this course. It's called a state machine. It has a memory, it has combinational circuitry, has inputs and outputs, and depending on the value in this memory, taken in conjunction with your inputs, you're going to get some outputs, and you'll also get new inputs to the memory. And there's a clock, and every time the clock ticks, whatever the output of the combinational logic says to load into the memory gets its new values in. And those new values go into the combinational logic and possibly produce different values here, as well as on the outputs. This is what your laptop is. This is what your cell phone is. It's just a big, huge, glorified state machine. Okay, so we'll dig into this in a lot more detail on Thursday. We'll start looking at specifics of this, and we'll look at some simple state machines and see how to analyze them. And this will lead us through most of the homework from Chapter 4. All right, I finished with like 10 seconds to spare, so have a good rest of the day. Shoot me questions or come to office hours on homework and lab, and I will see you next time.
Have a good day.
Thanks, you too.